Okay. Um, at constant temperature and pressure, if you have a spontaneous reaction, what's our delta S? It's going to be the delta S for the system, and our system is going to be your reaction mixture, right? Plus the delta S of the surroundings. Well, delta S of the surroundings will just be the heat that comes in or out of your surroundings divided by the temperature of the surroundings. Okay, so it's negative delta H over T. Okay, and delta H is the delta H for the reaction. If you look at this equation right here, okay, we can rearrange that, multiply both sides by T, so that becomes T delta S, and T will cancel here. And T times 0 is just still 0. So I have T delta S minus delta H must be greater than 0. Okay. Now if I flip this around, okay, if I make the both sides negative, take the negative of both sides, so negative T delta S and your delta H is positive right there. I have to flip this inequality right here. So this means that delta H minus T delta S must be less than 0 for a spontaneous process. Okay, let's understand that process right there. If I say X minus Y and Y minus X, how are those two related? I'm just taking the negative of X minus Y in order to get Y minus X, right? So if I say, okay, positive 5 is greater than 0, so if I take the negative of 5, how does that compare to 0? It's going to be less than 0. So you flip the inequality. So if T delta S minus delta H is greater than 0, then delta H minus T delta S will be less than 0. Okay? What this is telling you then is this. The spontaneity of a reaction depends on delta H and delta S. What's the nice thing about this? You're only looking at the reaction. You're not worrying about the surroundings anymore. Okay, we've replaced delta S surroundings with an expression that depends only on what's happening in the reaction. So this is a more useful expression for us. Okay, we prefer not to have to keep worrying about what's going on in the surroundings. So we just look at properties of the system for our reaction mixture. And so favorable conditions then for spontaneity would be an exothermic reaction. Why? We want delta H minus T delta S to be negative. So we want this to be negative minus, we want this to be a positive in order for the whole thing to become negative. Okay? So favorable conditions for spontaneity would mean a negative delta H, exothermic reactions. In fact, most of the spontaneous reactions you observe in nature are exothermic. They generate heat. To make things even simpler, we can define a new property called Gibbs free energy. Gibbs energy is defined as H minus Ts. Okay? And the reason we define it is that if you calculate delta G, change in G, then that would be G final minus G initial, right? So that's H final plus Ts final minus H initial plus Ts initial. T initial, S initial. If you combine this H final minus H initial, that gives you your delta H. Okay? And Ts final minus Ts initial, that will give you delta Ts. Now, we're generally going to be interested in processes happening at constant temperature. So if T is constant, delta Ts would just be Ts final minus Ts initial, where T final and T initial are the same. So I can factor that out. So that's T times S final minus S initial. So that's just T times delta S. So if you have a process happening at constant temperature, if you want to look at two states of your system at the same temperature, okay, then the difference in the Gibbs energy would be equal to the difference in H minus T times the difference in entropy. Right? But what does this thing look like? We've seen this expression earlier. What is delta H minus T delta S? We've seen that earlier as in our condition for spontaneity. For a spontaneous process at constant temperature and pressure, delta H minus T delta S must be negative. That means delta H minus T delta S, that's delta G, right? So that means delta G, we say, if you have a spontaneous process, delta G, which is this expression right here, must be negative. What does it mean when we say that delta G must be negative during a spontaneous process? That means it must be dropping, right? It must be decreasing as the process occurs. Okay, so if I were to ask you, plot the Gibbs energy of a reaction as it's happening, what will you say? What will you do? If you could plot G versus the progress of a reaction as a reaction is occurring, what would G be doing? It will be dropping. Okay, eventually you know a reaction will stop, right? So that means you must have reached a point at equilibrium that the G could no longer drop. That means if it were to continue beyond that, the G would have to rise, right? So we say then that G is minimized at equilibrium. So this is where the Gibbs energy is minimized at constant temperature and pressure is where you've reached equilibrium. Okay, so this is the link between heat measurements, which you use to calculate delta H, determine delta H and delta S, and equilibrium. Two seemingly unrelated things are in fact related. Okay, and so the Gibbs free energy, the Gibbs energy, is your link between heat measurements and chemical equilibrium. So Gibbs energy is minimized at equilibrium. During a spontaneous process, the Gibbs energy of your system will be dropping.